So we've learned a lot of different Laplace properties, and we've been working with Laplace transforms for a few sections. And I thought it would be good before we move on to just talk about why we did this and what it helps with. So you might be asking, like, why did we learn Laplace transforms? And mostly it's because Laplace transforms are useful for solving initial value problems, since taking Laplace of a derivative turns it into an algebraic equation that depends on initial conditions. And I'd even go further and say it's especially helpful if you have non-homogeneous parts. Because remember, when we solved non-homogeneous equations previously, we had to solve two different problems. First the homogeneous, then the non-homogeneous part. When we do Laplace, it happens all together. So having a non-zero function on the right-hand side is just one extra thing you have to take a Laplace transform of. It doesn't introduce a whole new side problem to what you're doing. A limitation is that we have only done Laplace for constant coefficients, because when we're taking that L of y's derivatives, it's already a pretty complicated function. We don't know how to deal with, if I wanted to have p of x times y, taking a Laplace of that. So it's not like every problem we've learned in class can be solved this way, but quite a lot can. And then given that's when we use it, it's also helpful to think about what are the challenges with this method, where do things tend to go wrong. And I would say that after you find that Laplace variable equal to some stuff, it can be hard to find a correct and simple inverse. Remember, we did so many problems where we had to do partial fraction decomposition, or in that section on convolution, we saw that depending on whether or not you spotted this special derivative trick could be the difference between that inverse taking you just a couple seconds versus taking you evaluating a whole new integral at the end of your problem. So that aspect of these problems can be tricky. We have learned a lot of properties, and I have them all written down here. What I'm going to do is I'd like to write them out for you all. Specifically so that we can talk about when we want to use Laplace transform properties. So I'm not going to remind you how to use these properties. I'll just write down one of the formulas so that you kind of have a memory of it, hopefully. So we learned the integral definition of Laplace transforms. We learned that they're linear, and we learned how to take Laplace of derivatives. And we also learned that there's a table that lists Laplace of a bunch of different functions. And for these first few things, I would say when to use them is integral definitions. Avoid, if possible. You can't help it if somebody makes you compute the integral definition of Laplace transform, but it should never be the thing you choose to start a problem with. Linearity, I hope you've used it so much that you can actually just do it without thinking. That every time you have a Laplace transform, you pull out your constants, you separate your functions. And then similarly, Laplace of these derivatives, they're very necessary for this class. We cannot write a differential equation without some derivatives. So just be careful about signs. And plugging in your initial conditions. So you will use it all the time, just watch yourself. And similarly, these tables of functions, we also just want to use all the time whenever possible. And really the only warning is that we have to be careful of constants. Sorry, you know, you have that there needs to be like a 4 in the numerator, so you do that fancy dividing by 4 and then multiplying by 4. Stuff like that. I had this thought that I was going to do a 2-column like I did for you all in the skeleton notes, and that's why all my words are crunched up here. But I actually can just go to a new slide, so I'm going to do that instead. And we'll write longer form on the next slide. So after that, we covered a bunch of properties that we said their common feature was that they related to translation. So this was that L of e to at f is f of s minus a. That was that L inverse of f of s minus a is e to at f, same thing. We had that L of f of t minus a u of t minus a is e to minus as times f. And that L inverse of e to minus as times f was f of t minus a u of t minus a. So when to use these properties? Let me make this one a little fatter, I guess. Normally it's skinny. So L of e to at times f, we just use if you have like an exponential of something times some stuff on your right-hand side. This can have some overlap with other things we've learned. So for example, like e to 2t times t, you could go ahead and do this way, or you could do with the multiplying by t property. It's kind of like your choice. And then the opposite one right here, L inverse of f of s minus a equals e to at f. You actually just use this to get back to little y. So when you start a problem, just remember the properties you use, and usually those same ones are going to come back at the end of the problem. This f of t minus a, u of t minus a, we just use when we have piecewise right-hand side of the equations. And then just sort of a note that it's a little tricky because we need to write f using u and that t minus a format. So we spent a bit of time on that, but it's usually what makes that type problem hard. And then the inverse, you just need to use that if there's u in the ODE. And then we learned today that we also need it if there's delta in the ODE. And then here, kind of like that formatting note, you just need to remember to plug in t minus a to the function and distribute whatever constants you need to make it correct. And so since it's super related, I'm just going to go ahead and put here with these two that we also learned today that L of delta of t minus t0 is equal to e to minus not A, sorry, we did t zeros. S times t0. And this property we're just going to use if there's a delta in the ODE. And these functions are always showing up on the right-hand side of the equation because our left-hand side is y, its derivatives, and constant numbers. So that would be when we use this property, and then we use that inverse property of u to get back out of it. I'm going to move to the next slide to give myself some more space, so please pause if you need the time. Forgot to change colors though. We talked about powers and derivatives. So that was our L of t to n f is minus 1 to n nth derivative of f. And our L inverse of this odd thing that we just have to be able to recognize is t to n f. So the forward property we use if there's t to n times something on the right-hand side of our ODE. This is the one that I said maybe there will be some ambiguity sometimes where you have like t to the power times e. Choose whichever one you like the most. And then the inverse property is probably one of the hardest for us to like identify when we use it. So go ahead and try to remember some simple cases of when you've taken it forward, what type of function came back out of it. Or remember, if you introduce this property when you take the forward Laplace transform of the ODE, you'll probably need this property to get back out of it to your little y. So, you know, remember common examples or just only use it after you've introduced it. And then we went over products and convolution. So we had that L of f star g is equal to fg, or that L inverse of fg is equal to f star g. And for these ones, the forward we don't use often. So if we're given some kind of integral that looks like convolution, we can take forward Laplace of it. But in terms of like differential equations, somebody's going to write down for you, this doesn't come up a lot. It's the inverse that ends up being pretty useful for us. So L of a product equal to something is super helpful. Something that you have to decompose with partial fraction decomposition can be addressed like this. Some of these derivative terms can be addressed like this. So this inverse can come up a lot. The warning being that the convolution to get to your final answer can be super lengthy. And depending on what you like, that might not be your preferred way to do a problem. I would do partial fraction decomposition probably before I would integrate trig functions, but that's because I don't like trig functions. And then here, just note that order doesn't matter. So you can pick the order for your functions that makes your life easiest. And I think that's all there really is to say about convolution. And then today we talked about periodic functions. And I'm not going to write out that formula again because we just did it. and this video is getting quite long, but you use it for periodic functions. So you just have to find that period and take an integral, so it's not that bad. I've written a summary of what periodic functions covers, which is the integral definition over that shorter period. So that is everything we have covered for Laplace transforms. I know this video is pretty long, but this section can just feel like a lot of different things that we're doing. So I really did want to give you at least the opportunity to see how they all fit together and start thinking about when you prefer certain properties over others.